Добрый день, доброго ранку, учительница. У вас микрофон закрыт, у вас микрофон закрыт.
Yes, thank you. Hello, let's go.
Что?
Let's go. Topic 7.
Окей, окей, окей.
Thank you.
Good day. Today we will explore one of the most important and powerful topics in SQL, the table join operation, known as join. Up to this point, we have worked with data within a single table, but the true power of relational databases is revealed when we start combining information from several related tables. We will learn how to obtain complex data sets, which are the basis for any sophisticated analytics or reporting in real-world systems. Before we dive into syntax and examples, let's outline the structure of today's lecture. First, we will delve into the mathematical foundation of the join operation, examining what a Cartesian product is and why it's crucial to understand. Next, we will thoroughly explore the most common type of join, inner join, and learn how to combine data from 2, 3, or more tables. Then we will move on to outer joins, which allow us to find not only matches, but also their absence. Finally, we will look at how to vertically combine the results of multiple queries using union and union-all operators. To understand how a DBMS, database management system, combines data, we need to refer to relational algebra. Imagine we simply ask the system to combine two tables without any rules. It will take each row from the first table and sequentially glue it to each row from the second. This is the Cartesian product. Let's consider an example. We have 2 students and 3 faculties. The Cartesian product will give us 6 rows, where each student will be assigned to each faculty. As you understand, this is absurd. That's why the key element of the join operation is the on clause, which acts as a filter, discarding all meaningless combinations and leaving only those where the values in the related columns match. Understanding this process is crucial for realizing why incorrectly written join instructions can be very resource-intensive. Before we look at SQL syntax, let's examine our source data. Imagine we have a very simple students table with 2 records and a faculties table with 3. Pay attention to the faculty ID columns. They are what logically link these 2 tables. Our goal is to combine them to get the student's last name and the full name of their faculty. But first, on the next slide, we'll see what the system does under the hood when we ask it to combine this data without any conditions. And now, see what happens if we ask the system to combine these tables simply by listing them in the query. We get a Cartesian product. As you can see, the system took each row from the students table and matched it with every existing faculty. Student Petrenko is now studying at 3 faculties simultaneously, which is of course absurd. This is where the essence of the join operation appears. Join is, in essence, the same Cartesian product, but with subsequent filtering using the on clause. This clause retains only those combinations that make sense, those where the values of the related columns match, from all possible combinations. Understanding that join is based on a potentially huge Cartesian product is crucial for writing efficient queries. Now that we understand the theoretical basis, let's move on to the most common type of join in practice, inner join. Its fundamental goal is to find the intersection of 2 datasets. It takes rows from 2 tables and returns only those for which the condition specified in the on clause is true. Typically, this condition is the equality of primary and foreign key values. Let's look at the syntax. We specify the first table in from, then write inner join and specify the second table. The key element is the on clause, where we explicitly state which field should be used to match the rows. On the next slide, we will apply this syntax to our students and faculties tables. Now, let's consider a more realistic example. We have a students table where, note, student Kovalchuk's faculty ID has a null value. This means he has not yet been assigned to a faculty. We also have a faculties table, which includes the law faculty with faculty ID equal to 3. Our task remains the same, to get a single list where each student's last name is accompanied by the name of their faculty. On the next slide, we will see how InnerJoin handles this task, taking into account the specifics of this data. And here's the query itself and its result. We use InnerJoin to join tables by the faculty ID field. Let's carefully analyze the result. As we expected, for students Petrenko, Ivanenko, and Sidorenko, the system successfully found the corresponding faculty names. But note 2 important points. Student Kovalchuk is missing. This happened because his faculty ID is null, and the system could not find a match for this value in the faculties table. The law faculty also did not make it into the selection, as there is no record with faculty ID equal to 3 in the students table. This is a key characteristic of InnerJoin. It returns only the intersection of data, ignoring everything that does not have a pair in the other table. By the way, in most SQL dialects, the word inner can be omitted, but its explicit inclusion improves code readability. It is very rare in real systems for all necessary information to be contained in just 2 tables. Typically, to build a complex report, you need to combine 3, 4, or even more tables. The mechanism for this does not require new commands. We simply apply the join operator sequentially. The logic is as follows. The first join creates a virtual intermediate result, and then we join the next table to it. Let's consider the task. For each student, we need to specify not only their last name, but also the full name of their group and the last name of that group's curator. As seen from the schema, to do this, we need to chain through from the student to their group and from the group to the supervising professor. On the next slide, we will write the corresponding SQL query. And here is the query itself. Let's break down its logic step by step. First, we join students and groups using their common group ID field. At this stage, the system forms a virtual table where each student's group name and curator ID are already known. Next, to this intermediate result, we join the professor's table. The join condition, g.curatorID equals p.professorID, allows us to find the professor whose ID matches the curator ID from the group data. In the final select statement, we add columns from all 3 tables. Note the use of AS aliases for columns. This is a good practice that makes the result clear, especially when column names might coincide in different tables. Thus, by sequentially applying join, we can build complex relationships and obtain enriched data. We saw that InnerJoin discards any rows for which no pair is found. But what if we actually need to see these lone rows? For example, to find all students who have not yet had a faculty assigned, or to find faculties where no students have yet been enrolled. This is precisely what outer joins, or outer join, are for. Their main difference is that they include rows from one of the tables in the result, even if there are no matches for them in the second table, filling in the missing data with null values. We will cover 2 main types, left join and right join. So, the left outer join, or left join. Its name speaks for itself. The left table, the one specified in the from clause, is primary for it. The operating principle is as follows. The query is guaranteed to return absolutely all rows from the left table. Then, for each of these rows, the system will try to find a match in the right table based on the condition in on. If a match is found, great. Data from the right table is added to the result. If there is no match, the row from the left table still remains in the selection, but the columns from the right table will be filled with null values. The word outer in left outer join is optional and usually omitted for brevity. Let's look at how this works in practice on the next slide. Now, let's see how left join solves the same problem that inner join couldn't. Recall, we need to get a list of absolutely all students. We write an almost identical query, but replace inner with left. Look at the result. Unlike last time, student Kovalchuk is now present in the selection. Since the system, taking his row from the left table, students, could not find a match for him in the right table, faculties, due to null in faculty ID, it simply filled the faculty name field with null. This makes left join an ideal tool for finding entities that lack something, customers without orders, students without curators, etc. Now, let's consider the right outer join. Its logic is absolutely mirrored to left join. The primary table is now the right one, the one specified after the right join keyword. The query is guaranteed to return all rows from this table. For each row from the right table, the system will look for a match in the left table. If found, it will add the data. If not, it will keep the row from the right table and substitute null for the columns of the left table. It's worth noting that any query with right join can be rewritten as a left join simply by swapping the tables. Many developers prefer to use only left join to maintain a consistent code style, but knowing and understanding right join is also necessary. Now, let's apply right join to solve a different problem. We need to get a list of all existing faculties, even if no students are currently enrolled in them. The query is very similar to the previous ones, but the keyword here is right join. The right table, faculties, becomes the primary one. Look at the result. All faculties with students are displayed correctly, but now the law faculty is also present in the list. Since the system, taking this row from the right table, found no match for it in the left table, students, it simply filled the last name field with null. This example clearly illustrates the mirrored logic of right join compared to left join. Up to this point, we have considered join operators, which, figuratively speaking, expand tables by adding columns from other tables. This is horizontal combining. However, sometimes a different task arises: to take the results of two completely independent queries and stack them one below the other, i.e., combine them vertically. For this purpose, SQL has the union and union all operators. For such a combination to be possible, the queries must be compatible. This means they must return the same number of columns, and the data types in these columns must match or be compatible. For example, number with number, string with string. Next, we will consider each of these operators separately. Let's consider the first operator for vertical combining, union. It takes the results from two or more queries and stacks them one below the other. Its most important characteristic, which you need to remember: union performs a deduplication operation on the result. This means that if an identical row appeared in the result of the first query and then again in the second, it will only appear once in the final selection. To perform this deduplication, the database system needs to do additional work under the hood, usually sorting and comparing rows. This makes union somewhat slower than its counterpart, which we will discuss later. On the next slide, let's see how this looks in practice. Now let's look at a practical example. Imagine we have two tables, students and PhD candidates. We need to get a single list of last names of everyone studying, without repetitions. We write two separate select queries, one for students, the other for PhD candidates, and combine them using the union operator. The key point here: if a last name, for example, Petrenko, exists in both tables, union, thanks to its duplicate removal property, will include it in the final list only once. This is exactly what we need to create a unique list. Now let's look at the union all operator. It does almost the same thing as union. It vertically combines query results. But there is one critically important difference. Union all does not bother with searching for and removing duplicates. It simply takes all rows from the first query and appends all rows from the second below them, as they are. Because union all does not perform this resource-intensive deduplication operation, it works significantly faster. Therefore, there is a golden rule for developers. If the uniqueness of the result is not mandatory, or you know for sure that there will be no duplicates, always use union all for better performance. On the next slide, let's see when such behavior might be useful to us. Let's consider a practical case. We need to create a single list of email addresses for a mailing, which should include both students and professors. Imagine a situation where the same person can be, for example, a PhD candidate and simultaneously work as an assistant in a department. In such a case, they should receive two different messages, so it's important for us to keep both their records. We write two separate queries and combine them using union all. If the email petpetrenko@univ.edu exists in both source tables, union all will return it twice, which perfectly matches our task. This is an excellent example of when the faster union all is not just an optimization, but also a logically correct choice. Thank you all for your attention. Today, we have covered one of the fundamental topics of SQL, which is the basis for building any complex queries. The ability to correctly combine data from different tables is a key skill for any specialist working with databases. In the next lecture, we will continue to expand our capabilities and talk about aggregate functions and data grouping. This will allow us not just to retrieve data, but also to analyze it, count quantities, find averages, maximum and minimum values. See you next time.